Thank you, and thank you for having me at ScopeX. It's a pleasure to be here. I'm going to talk about impacts and collisions in the solar system. In order to set the stage for that, let's just back up a second. This is, if you look out up at the night sky, this is from Mark Kelly. I'm staying at one of the guest houses there, and look up one of the most common sites that we all love to look at is the Orion Nebula. If you take the Orion Nebula and you zoom in here, this is one of the early Hubble Space Telescope images. This is in the visible, and you can zoom in toward the trapezium cluster here in the middle, and you see the bright O and B stars in the trapezium cluster here glowing in ultraviolet light. And you zoom in a little bit more here, and you see all these little baby solar systems, things like these here. And you see these systems. This is 200 astronomical units across, so about the same size as our own solar system. And what these are very violent places. These are places where the formation of the solar system is dominated by collisions, and where you have dust that is colliding with each other, it sticks together, and you have rocks that collide with each other and stick together. You're starting with a dust cloud, and you end up with something like the solar system. In that process, you end up having collisions over and over and over again. And so there's billions of countless collisions that go into making up the solar system. These go into making up the small planets, into the big planets, into the Earth, into everything in our solar system. And so the solar system is based around collisions. Now, that's in the past of our solar system. But in the present, collisions are still omnipresent. This is a picture of the moon. Up until the mid-50s or 60s, it was actually believed that all these circular features on the moon were volcanic features. They were thought to be volcanoes that had caused craters on the surface of the moon. And then in the 50s and 60s, with the Apollo missions and with other work on the Earth, it was realized that no, these are actually due to impacts over the course of billions of years that have literally covered the moon so that it's saturated, so that if you put more craters down on it, you cover up the old ones, and so it can't hold any more than it has right now. It's like a bucket that's full of craters. Any more you put down there, it gets rid of old ones. And many other surfaces in the solar system are also saturated with craters. They're so full of them. Typical craters that you see up here, something like this. This might be 50 km across. And it's, of course, not just the moon that has craters on it. If you look at the history of the Earth, how many people have been down to the Vredefort impact site? All right, good. So you can trace this out. This is the largest well-preserved crater on Earth and the oldest. There's one older one which is out in Russia, but it's very hard to see. With this site here, it's very easy to see here. You can sketch in circles here some of the rings that are caused during that impact. These are just some of the inner rings because these go out to several hundred km in the geological record. The reason why this is still well preserved is because it was gigantic and it was a long time ago. This was a 300 kilometers originally, and you can still see it pretty well now in some parts. So if we zoom in a little bit here, we can see Paris there. You can see the crater rim here, and there's a road here. You can actually drive down from Potch, as many of you may have done. And so I was down in giving a seminar in Potch a couple months ago, and I took the day afterwards and drove down into the crater and walked around here. And it's so cool because you can actually walk on the rim and see into the impact site there, or see into one of the other inner rims of these concentric rings there. Ground zero is at the center there. You want to see what ground zero looks like? Center of an impact site? Yeah? Okay. Let's see what it looks like. So a lot of erosion and geological processes have shaped this in the past 2.2 billion years. It's a little bit hard to see it. This is an impact site, but I promise you. This was something on the order of 10 km across. This was a much larger impactor than what killed off the dinosaurs. We see a history of other sites around the world. This is one of the most well-known, which is a Barringer or meteor crater up in Arizona, outside Flagstaff. 1.3 or so km across. It's in the Arizona desert, and it's very young, which is why it's those two things, is why it's well preserved and famous. It's a beautiful place to go to. I actually walked down into the center of this with Eugene Shoemaker, who's the well-known geologist who sort of started the whole field of impact craters and studying them. And people have been to Tswang impact site as well. Also worth going to. It's very nice. It's about an hour north of Pretoria. A little bit smaller than the meteor crater in Arizona. A little bit older, so it's not quite as well preserved, but still, it's a beautiful site, and I recommend going there. One of the other famous ones on Earth is the Chicxulub impact crater. Chicxulub is named after the Mexican city in the Yucatan, which is close to this. This is some 65 million years ago. This is I guess a similar size impactor to the Vredefort, a little bit smaller. And you can't see the crater very much if you're walking around anymore. But in the gravity field data, you can certainly make it out here. This part over here is the ocean. This part is the land of the Yucatan. The town of Chicxulub is right there. And so this is about 65 million years ago. The Earth has had a history of, there's probably been dozens of these sorts of mass extinction events over time. And so what happens here when you have a gigantic impact is that you have essentially it's a nuclear winter where you have a lot of smoke, you have a lot of dust, which is lofted into the atmosphere. It goes very high up. It stays up there for a long time. It cuts off light, which feeds plants. It makes smoke. It kills things, and so forth. And so you have a global event lasting not that long in a global sense, or geologic sense, lasts maybe a year or so, but that's long enough to kill off, to destroy the food chain so that many of your species are going to die. The largest impact that we've probably had on Earth was very soon after the Earth's formation, when Earth was formed by something the size of Mars. Gigantic, can you believe it? And this spewed off enough material from the surface of the Earth, spewed it off into space, and that's what formed the moon. And so what happened here, you have this Mars that's coming into the Earth, spews off all this material, goes into orbit, and it doesn't take long, not more than a couple of hours until the moon has kind of accreted as a blob out here. And then within a couple of months, all this other material has fallen back to Earth, and you have a moon in orbit around the Earth. So we've seen these impacts for a long time, historically, but they're still ongoing. And about 18 months ago in Russia, there was an impact that was seen by many of the residents of Chelyabinsk, Russia. And let me just...
Нихуя себе, это что такое? О, нихуя метеорит, блядь.
Внимание,
Ебануться. Нихуя себе.
This is actually in one of the lakes outside of Chelyabinsk, where part of the impactor was actually recovered from. And what was amazing about this is it was so well observed. I mean, there were literally thousands of people with their cell phone videos and with their security cameras and so forth that were able to observe this and study it. That its path can be determined very well. It can be traced backward, and you can see exactly where this is coming from, because you know also where it ended up, you know where it was shooting across, and so forth. So you can do a lot of great triangulation on this trajectory. And so we know this. We can trace this back. This is not an actual object that we knew of beforehand. This is smaller than our detection limits for near-Earth asteroids, but it's a pretty similar orbit to several that we've known about. So it's probably a similar parent body to this one called 1999 NC43. This thing has a semi-major axis where it crosses the Earth's orbit like many near-Earth asteroids. And from the studies of the tail and of the airburst, you can get an estimate on its mass, 13,000 metric tons, about a 30-meter diameter, exploded about 30 km above the ground. No one was killed in this, which is pretty remarkable. However, it did hit over a generally populated portion of Russia. However, about 1,500 people were sent to the hospital, and most of these are people who are doing probably what you and I would do. They're like, "Oh man, what is that up? There's this huge bright thing out there," and they go up to the window, and then they stick their face at the window, and then 10 seconds later, the windows get blown out. And so that's what the vast majority of these damages have come. There's one woman I think who hurt her spine. And a lot of buildings that were damaged, many millions of dollars. This is certainly the largest known object to enter the Earth's atmosphere in the last century, and it's the best observed one ever. And so, although this is not one that we knew about beforehand, we have seen there's been a very small number of objects that we knew about beforehand, and then we observed to land on Earth. This is by far the best observed one that has been seen, and it's really great that we've been able to recover part of this as well. I said this is the best. This is the largest one in the last 100 years. It's not the largest one in the last 105 years, because this one here was the Tunguska impactor, which hit Russia also in 1908. Is the largest one which has ever been recorded. Russia wasn't as populated, and this is a less populated area of Russia at the time, so it wasn't observed directly by nearly as many people. And so this is the Tunguska event over here in Russia, and Chelyabinsk is just right over here. It's pretty close. And you're thinking like, oh man, lightning doesn't strike twice, right? But but hang on, we have the two largest known impactors ever, and they both hit northern Russia here. What are the odds of that happening? They're right next to each other. I don't think that Russia has anything out for it. So this is entirely just a statistical fluke that they both hit right next to each other. But it's pretty interesting. I guess if you're not Russian in particular. So these are a fluke that these two have hit next to each other, but it's not a fluke that we have lots of impactors on the Earth. I mean, we get hit by about 40 tons of material a day. In large part, this is mostly sand grain size stuff, millimeters, couple millimeters, the sort of stuff that you see as meteors and shooting stars. But this is the power law distribution, and so although there's a large number of the very small things, there's also a small number of the very large ones. The largest significant one that caused mass extinction was the KT impactor, KT meaning Cretaceous-Triassic, at the 65 million years ago. And we know that things like that have gone on many times in the past and will continue in the future. Over here, these are just a couple of the pictures from the Antarctic Meteorite Survey, which the National Science Foundation in the States runs. And a lot of these studies of meteorites are done. Well, if you walk around your farm and you pick up a rock, it's probably not going to be a meteorite, right? It's probably just going to be a rock. But if you're walking around Antarctica and it's kilometers and kilometers and kilometers of pure ice, there's no mountains around, and you run into a black rock, what do you think it is? It's probably a meteorite. So it's not that Antarctica gets hit by more meteorites, but they have a longer lifetime there, and they're easier to identify. And so the National Science Foundation sends down groups of people with snowmobiles every year to just cruise around the surface of Antarctica and pick up these rocks. And so we get a lot of science about the composition and history and makeup of what went into the solar system, what went into making up the Earth, and the current composition of the asteroids from these meteors. Let me just show you. So I told you it's a power law. Let me just show you a quick distribution here of what it looks like. So over here I've plotted the diameter in kilometers versus the number of bodies that we have, and this is a rough estimate of the impactor population on Earth. And so you see that we have, on the large bodies here, we have a very small number of them. And for the smallest bodies here, off at 10 meters, we have a great number of them, hundreds of millions of them, which are of the population which can hit the Earth. This is the population, the total population in the solar system, which is near the Earth now and could potentially in the future hit. And also with the impact interval over here. And so we can put a couple of objects on here. Here's the Chelyabinsk impactor off at 10 meters, 20 meters or so. With it, we figure things like that hit about every 100 years or so. Sometimes these are going to hit in the ocean, of course. Sometimes they hit over continents, but we have enough. We have enough monitoring now that it would probably be hard to miss something if it hit over the ocean. There's the Tunguska impactor, which is a couple times bigger than Chelyabinsk, so a couple times more rare. Let's put the KT impactor down here, way on the bottom here. Also the Vredefort impactor of comparable size. We can also put there was one of the most well-known airbursts over the ocean. It was actually off the coast of South Africa back in 1963. And that was even it was a little smaller than the Chelyabinsk one, but one of the other largest that we've had in the last century. For reference, we can put Hiroshima up here as well in megatons. And so these large ones. Let's talk about the impact hazard here to Earth, because some of these things are dangerous, right? That's why we're talking about them. So these large ones, which I've kind of shaded in green here, the light green. Anything over on this side are large enough, they're easy enough to detect. So we've probably found almost all of them. We're not going to, if something the size of Mars is coming at us, right, it's not going to be unknown. We've been looking at things the size of Mars for thousands of years. So, one of you would have discovered it. So Mars, we don't have anything which is big out there. And so we've kind of discovered everything which is bigger than a kilometer or a half kilometer, something like that out there. And it's on the order of thousands of bodies, which are out there like that. And then you go on the other end, on the very small end of things, and most of these are not very dangerous because either they're just not that much mass in the first place, or because they're not much mass, they break up in the Earth's atmosphere and they don't hit the ground. Chelyabinsk is right on that line where it made a lot of damage on Earth, but it didn't make a big crater on the Earth. It just made that hole in the ice where one of the chunks hit. But it's things like Tunguska here that are the real problem. And so these small ones aren't a problem, these big ones aren't a problem. It's just this area right in the middle, which is actually the problem. So we can draw this curve here. And so this red region in here is the area which they're not detected, and they're not small enough, so they're dangerous and not yet detected. And so if we want to do any work into assessing how dangerous these are to Earth, it's this middle region of objects which we need to take a look at. So the circles here show the total population out there, the estimated total population. And the solid line here shows the detected population. And you can see that we've detected all of these over here, and then there's kind of a fall off down here in this region here. So we talk about the asteroid belt. That's where all these things are. The asteroid belt has somewhere on the order of 500,000 known asteroids in it. This plot is a little bit deceptive here. It makes you think, here's the Sun, Mercury, Venus, Earth, Mars. This makes you think that if you fly through the asteroid belt, you're likely to hit something. It's not. It's just because the pixels here on the display are too big to actually show it the side of an asteroid to scale. In reality, you can fly your spacecraft about 1 million times back and forth in the asteroid belt, right through the center of it, without having a risk of actually crashing into anything. There's a lot of asteroids in there, but there's a lot more empty space. So we have this 500,000 main belt, they're called main belt asteroids. We have about 10,000, 11,000 what are called near-Earth asteroids, and these are ones so these are the ones, this is Mars here, and so these things here, these green ones don't hit us, but there's some smaller ones which I'm sorry it's just a little hard to see on this display here. There's many of these that come and pass near the Earth up here. We know about 10,000 of those, and then there's some subset of those, which are the ones which are in this dangerous regime, kind of from 30 meters to 150 meters, where we haven't found them yet, but they're too big to burn up in the atmosphere. And there's some fraction, about 1,500 of those that we know of now. And on these large ones, we're basically complete. We know about all of them that exist there. But on this other range, there's a lot. We've only found a couple tens of percents of the actual bodies out there. So there's a lot more out there that we want to detect and know about and characterize, so we can know their risk. So how do we go about detecting these? NASA has actually had a program for the last 10 or 15 years or so, which is called the Near-Earth Object Observation Program, and it has done a fantastic job at detecting a lot of these. There's several NASA-funded telescopes. There's one in New Mexico. There's one in the pair in Australia and Arizona, and then there's one in Hawaii, which are parts of this program. And basically what these do, these are pretty moderate-sized telescopes. These are a meter or two, and they're fully robotic telescopes. So you just turn them on, and they go out, and they have wide field cameras, and they just take an image, and then they take another image, and then they look for anything in the ecliptic which is moving. And most of the things that are moving they've seen before, but sometimes they will find ones which they haven't seen before. And usually it's a couple per week that are new. A dozen per week, maybe, something like that are new objects. And then those get added to the database. And so there's been a lot of work. We're mostly complete down to the 1 kilometer size, and the work now is on extending this to smaller and smaller sizes, down to 100 meters, 150 meters, which is where the real danger zone is. What is this danger, anyhow? How many people know someone who's been killed by an asteroid? Anybody? Okay, nobody, no close friends. Okay, fine. Yeah, so historically, actually, the total number of people ever killed that we know of by an asteroid is right at 0. So that's an average of 0 per year. Cool, easy math. But what's the expected value integrated over time? So you figure that we can get the number per year just by dividing the total number that are killed in an impact divided by the number of the frequency of those impacts. So now if you have a global impactor, if you had something which is the size of the KT impactor, let's say it would kill off the entire population of the Earth. Okay, that's 7 billion divided by 70 million. That's pretty easy math too. That gives you an average of 100 people per year that are killed by asteroids. That's a pretty big number, and it's quite a bit bigger than 0. And so, but the math is a little bit funny because this is a low probability, but high consequence event. And so, how do you really? This is the sort of thing that insurance actuaries would get all excited about, as far as how do you calculate the what to do with this. One thing you can do is just compare this to the number of deaths from other things. Malaria, of course, is the biggest maybe easily solvable cause of death. Hundreds of thousands of people per year. Commercial airplanes, sharks. But airplanes here is interesting. I mean, because this is about 100 per year, and this is about 100 per year, and so plausibly, you could make the argument that if we spend billions of dollars per year on airplane safety, it's not crazy to spend some money on protecting ourselves from the asteroid risk as well. So about a year and a half ago, Congress charged NASA with what they called the Asteroid Grand Challenge. And the job there, Congress says that NASA must, quote, find all asteroid threats to human populations and know what to do about them. And so by threats to populations, what that was defined as is things which are larger than about 100 meters. We want to characterize them and determine a way to mitigate them. This doesn't mean let's actually mitigate them right now. Part of the task is not to actually go and blow them up, but to study the different ways in which you could divert these and move these if you determine that's the best thing to do. And so, historically, where we are here, this is the number of asteroids over time, this is where the big asteroid surveys kicked in, is where the total number of asteroids started to really skyrocket. And here, but we're on these large NEAs, on these other NEAs. This is where most of the effort is going to go into, is getting these values complete to the smaller and smaller sizes. So it's kind of cool that South Africa can play an important role here. I was out at the SAAO observatories at Sutherland a couple of months ago. We spent a week observing asteroids and NEAs. NEAs mean near-Earth asteroids, things that pass within 0.3 AU of the Earth. And we spent a week observing them out there from the 1 meter telescope at Sutherland. This is the 1.9 meter that used to be in Pretoria. This is the 1 meter here. And so there's a couple of different ways observationally that you can be involved with these studies. Okay, so one of the things is in terms of discovering new NEAs. What this basically requires is wide-angle robotic telescopes. If you look at the inventory of telescopes that South Africa has, none of them are wide field, and there's only a small number which are robotic and automated involved. And so, as far as this goes, South Africa is not very well set up. But there's a lot of these asteroids they're detected, and then they are never observed after that. And there's a lot of studies that can be done on these follow-up observations for instance, to constrain how fast these are rotating, to constrain what their composition is, to constrain better what their orbits are, and so forth. And these are things which can be done from very moderate class telescopes, meaning half meter to meter to 2 meter, can be done very well from South Africa. And there's a significant geographic advantage that South Africa has here too. Let's look at a map of the Earth here, and this is just a plot of. This is an actual plot from the Minor Planet Center, which is the group in the U.S. which kind of catalogs and puts together all these observations of what are called minor planets, which is the technical word for asteroids. The dot just means they've received some observations from the telescope at this site. And okay, so there's tons of observations from the States. There's lots from South America. There's a slew of them from Europe. Some over in Japan, a couple over in Australia there. One in the middle of the ocean out here. What's this here? Reunion. There's a telescope up there. But with the exception of that one telescope there, we have this gigantic hole 11 time zones wide. And what? There's no observations in here? Come on. So this is actually a really huge opportunity for South Africa to become involved with. And the reason why this geographic advantage is great is because a lot of these objects are going to be observed from, they have essentially a random position in the sky, but all these northern hemisphere observatories can see all the northern hemisphere objects, and who's going to see all the southern hemisphere objects, especially if they're up only during the daytime in Australia or in Chile. South Africa is perfectly positioned for that. So there's a huge gap in observational coverage of asteroids, and it's centered on us, which has a lot of telescopes, so it's great. So this is something which I'm working with a couple of students at University of Pretoria. We have some more observing time scheduled on the 1 meter telescope, and also on the Las Cumbres telescope, which is a pair of 1 meter telescopes, which is sited also at Sutherland. This is a global network of telescopes that South Africa is participating in. A lot of these observations also can be done by amateurs with something, with a half-meter size telescope or so, taking light curves, where you just looking at the brightness variation of these asteroids over time as they rotate, or doing astrometric follow-up observations, where you're refining the position of these stars relative to the position of the asteroids relative to the background stars. Where you have ready access to telescopes and a lot of glass, dark skies, and unique geography. This is the 1 meter telescope that I was working on out at Sutherland. Why am I outside taking pictures? It's because the humidity was too high. We had 7 nights of observing there, and we actually didn't get to open the dome for a lot of that. I think we had 3 nights where we opened the dome partially. At least it wasn't cloudy this night, but the humidity was too high, condensation was too high, and so we couldn't open up. But there's the 1 meter telescope there. It's not a very wide angle telescope. It's about a 10 arc minute field of view. So this is good for getting photometry of these asteroids. It's not very good for searching for them, because for that you need a much wider field of view. But here's just for kicks. Here's a movie of one of the asteroids that we have. This is about an 18th magnitude object here, 17. This is just a couple hours of observation here. You can see it right there relative to background stars. This is a basically unremarkable asteroid called 3288 Seleucus. Why we chose this is because it was one which was at its periapse, so it was close to the sun and close to the Earth, and it was above us at the right time, and so we could observe it. And asteroids, there's because there's thousands of these out there, and the vast majority have not been remeasured, they've not been reobserved since they've been detected. There's often ready targets out there which are waiting to be observed. And so that's what we did here. This is the sort of light curve that we were trying to get. We don't have enough data on this one to put together a long light curve. But this is on the period of a couple of hours, how it rotates. This one is actually a binary, which is causing these dips here as the satellite of the asteroid is going in front of it. Some 5 or 10% of asteroids are probably binaries. This is one of the other nights where these are actually the car headlights from one of my Polish colleagues there, and she was driving back down to the hostel from Sutherland because it's too cloudy up there. It made for some great photos as everything was filtering through the skies, through the clouds. But we didn't have great weather that week. It was better weather than the last time I was up there, which is this is salt. How many people have been up to Sutherland? Good. Okay. So I didn't expect to get stuck in a South African blizzard on my first observing trip up here, but man, it was cold up there. So this is our asteroid grand challenge. Detect all asteroids, detect all NEAs greater than 100 meters, characterize them, and then determine a way to mitigate them. Let's look at what we can do to mitigate them. How do you actually go about moving an asteroid if it's up there? So here's a little sketch of the, here we've got the sun, here we've got the Earth. Let's say you've got an asteroid coming in, or you're looking at not coming in, but you know the orbit of an asteroid, and that's because you've observed it a number of times. And it's on a Keplerian orbit around the sun. And usually how these, if you have, it has one period, and the Earth has one period, and the orbits are not quite circular, and so this orbit is going to precess a little bit. So in our fixed field of view, what happens is that it goes on kind of a loop-de-loop orbit where it slowly is changing its orbit, so that you have a bit of headway, a bit of knowledge before it's going to finally have an orbit which is going to take it across the Earth there. So it passes the Earth, and then it's got a closer pass of the Earth, and then it's got a closer path of the Earth, and each of these orbits, remember, takes a year or two until finally you have something like that. And so in general, this isn't the case where you where you just look up and there's something which is coming in at you, which you've never seen before. That happens with comets. Comets are start off way, way, way far away in the Oort cloud, and they are on hyperbolic orbits, which means they're basically just coming in on a straight line to wherever they want to come. These asteroids are on circular orbits, which are based in the asteroid belt or near us, and so with them we have a much longer advance warning. And those are much more common than comets that come in from great distances. And so we have all this advanced warning. So what can we do about that? Let's say this comet is coming around here. This asteroid's coming around here. It's over here. If we can just move this thing a little bit, put a spacecraft or a rocket or something like that on it, just move it in its orbit a little bit, and then keep it going. It changes the position of that orbit, and then it keeps going, and then it's on a circular orbit or an orbit which is not crossing the Earth. That's probably dynamically the easiest way to do things. And a couple of different ways you can do that. You could just put a rocket on there. That's fine. Bolt it on there and use a chemical thruster. It doesn't require a lot of thrust to move these things because a small change over here makes a much larger change in its position over here. You could put on what are called ion drives. Ion drives are what are used on some spacecraft these days, where it's essentially it's an electric drive that puts out a very high thrust per mass. It's a very high-speed thrust that comes out much faster than the traditional chemical thrust, and so there you can get even more oomph. How these work is they have a low thrust over a long period of time, which gives you a bunch of integrated kick. And then you could use something which is even more tricky, which is you just use solar radiation pressure. The sun is putting out photons, which can be used, which actually create a pressure. And so if you were to do something fancy like paint part of your asteroid white, paint part of it black, do that in a careful way so that you can control the radiation pressure on the asteroid just like you would control it on a spacecraft. You see how radiation pressure can tilt the spacecraft on solar panels or the solar sails. You can do that with asteroids as well. There's other ways not to move these things. It's probably send Bruce Willis up there is not the best plan, because what you really don't want to do is blow this thing up into a million objects with an unknown trajectory, because many of those are going to be small enough. But what if you're left with one big chunk which has had its orbit changed so it's headed right toward Tokyo? This is not the best idea. So there's some talk at NASA about what's called the asteroid retrieval mission, and I have just a quick movie to finish up with about the asteroid retrieval mission. This is a proposed future mission. This is not something which has been funded or really anybody has spent a lot of effort studying yet. But the idea here is if we did want to send humans up there to look at an asteroid, to study it in person, to look at what you would do to move it. Let's do this just in a test case with a very small asteroid, meaning a couple of meters, not a couple of km, but a couple of meters. And here's a rough concept of what you might be able to do with that. So this isn't a mission we're going to fly yet. Right now, we're in the state where we can do so much from telescopes, so much from the ground, both from telescopes here, from amateurs, from other larger telescopes across the globe, and that's really the phase this research is in now. So let me just leave you with a couple of thoughts here. I hope you can appreciate that one of the things we can do now is we're starting to be able to quantify what the impact risk to the Earth is from these near-Earth asteroids, and it's a non-negligible risk. And there's so much good science and so much studies that can be done to these out there. The vast majority of these have been detected but not followed up on. So there's so many good targets to explore, and South Africa is such a great place to do this work from. So thank you so much.
Thank you. We've got time for a couple of questions.
You were telling us that the vast majority of these objects discovered have not been studied. Does that mean that the orbit is still not known of these objects?
Basically, they've been studied. They've been kind of observed, in a couple of images. If you observe in about 3 or 4 images, that's enough to get a rough estimate for their orbit. But it's a rough enough estimate for the orbit that you might not even actually be able to find them again with just those orbital elements. And so what's important actually is studying these things like soon after they're discovered, like a week after, 2 weeks after, and or on some of them you can study them months after if you just have a little bit of patience to find them. The other thing which is important to study with these is their rotation rate and their spectrum. And for the vast majority of these, those have not been studied at all. So they're studying their light curve, gives you their rotation rate, gives you their shape, it tells you what their binaries are not, things like that. That's where you get the basic understanding of their physical properties. Yeah.
The two impacts in Russia over a period of 200,000 years. Was the chemical composition of the asteroids?
The two impacts in Russia over the course of 100 years. Was the chemical composition similar? We don't know anything about the Tunguska one because I don't think that anything has been recovered there. With the Chelyabinsk impactor last year, parts that have been recovered. It's a meteorite. It's not a comet. It's a relatively unremarkable meteorite. They're unremarkable asteroid that caused it. So in general, they're similar. Yeah, but it's not like they came from the same parent body. They're not identical. Yeah.
When did you say that the Fredefort asteroid hit?
2.2 billion years ago was the
Billion
Fredefort
years ago.
impactor.
Okay, that makes sense because I assume that caused a global serious event much worse even than the one that.
It did, but luckily there wasn't much living then. I mean, the Earth was at that point it was basically being covered by algae, and that algae's job was to take all the CO2 out of the atmosphere and crank up the oxygen in the atmosphere so that everything else could start living. But it was pretty much like one species living on Earth. It was living all over, and if you kill off half of it from an impactor like that, the other stuff will take over pretty quickly. So it wasn't that big a deal.